Okay, so let me do a quick attendance check. Okay, if I may pronounce incorrectly. Dewi? Okay. Menace? No, not yet. 简称 not yet. 佑嘉 OK. 郑飞 OK. 盛斌吗 OK. 冠中廷伟博如永杰这怎么样？这怎么样？不会念的，教一下。这怎么念？第二个字怎么念？忘记了。奶哦，这是念奶哦。你们看不到OK。
他直接把投影机先拉到底点，所以电脑应该。
不能播哦。
对，因为他说他下面还有是坏掉。
君臣 OK。哇，怎么样？玉成嘛 OK。右华思乔艳红吗？还是明？我念一个门在一个红，是吗 ？OK。没有，奕晨 OK。林生 OK。冠宇，你是哪一位？艳红 OK 冠宇 OK。阿 Z 那也。Rati 那也。Rayhan 那也。范明有。大家 OK。威豪 OK。So we have on the system there are 25 students, and last time I checked there are 12 of mine, so we can have actually I think for the doctors they can be one person in a group. So 13 and 14, if that's the case. Yeah, so we have if we don't count the doctoral students, then we have 11 master students. 11 of mine, 11 master students, and we have the other 11 graduate students, master students. So I will randomly assign the master students from other lab to team up with my students. So let me show you on my sharing screen. Let's do the grouping. Here. Yeah, so right here I already let me just reorder. Okay, so we have to change. So from group number 1 to 11, they are the master students from my lab. So 12, 13, and 14, you are the 3 PhD students. You guys can be one-person group. So there are these students who are not from my lab. I will just randomly place you. So I will do that right now. Yeah.
My name is not on this.
You're not in the list. Okay. Were you here last time? Not yet. Oh, so first time here.
Yes.
Okay, yeah, that's fine. What's your name again? I come here. Chinese or English? Oh, I'll just type try. Okay. So let me. Okay, so I just randomly generate some numbers, and then this is a random sort. So that's a group. So now we have 12. So I guess. How about this? The 12th person worked with the gel, and the 2 PhD students work. No, that would be. The PhD should be separate. Yeah.
Sorry for Rehan. For Rehan Fadri, I think he will not join.
Who?
Rehan.
Rehan. He.
Yeah.
Oh, good. So that solved the problem. Okay, thank you. So then screw up my random process. Okay. So that was not the final. And this is the final. Okay, so I'll just paste them here. So your group 1, Tron, you are group 2, Youhua group 3, Yeming group 4, Kati group 5, Zhong Boru group 6, Shenbing group 7, Siqiao group A, Yichen group 9, and then Guanyu group 10, Youjia group 11. Okay. So perfect. Now I will regroup you guys, reorder you guys. Okay, so these are the grouping. Okay, so the Tajeo, please update this to Facebook later on. Okay, so every one of you will be working with my student, and we will talk about projects later on. Okay, so for today's lecture, I will focus on the course material. Okay. I think my laptop won't it's not having enough power. It's not. Maybe I turn off something. Okay, I turn off something. Because it's not charging. So later on it will be out of power. Let me turn off something. Turn off. Okay, turn off Dropbox. Turn off line. Snag it. No, it doesn't help. It's not charging, so later on it will be out of battery. Let me try this. No, it doesn't. Let me make it like this. It doesn't charge. Okay. So maybe I will just use my iPad for now, and I will let my iPad charge. My MacBook charge. So later on when I do the programming, I can share the process of programming to you. So let me do that. In that case, I will turn off the OBS. So I need to rely on that GoPro. Turn off this. Yeah, just let it charge. Okay, great. Back to today's lecture. Today is 24th. So we will be doing unconstrained optimization, which means we only worry about minimize f of x. And sometimes we will put the design variable underneath the minimization sign. Why do we do that? Because sometimes we may have a function where you may have some parameters, but they are not variables. So you may need to specify what are you varying in your optimization process. So sometimes you may see this, which is clearly specifying what are the variables in the problem and what are other parameters, but they won't be changed during the process. And here I never put any vector sign on any symbol, which means they are just single variate design problems. But in optimization, we may have multiple design variables. So here's an example of how you can handle multiple variables. Right? Then you can put them in a vector. I will start with the simplest problem, one-dimensional Newton's method, which I have shown you last time, but I will do some proving today. So in a one-dimensional problem, basically you have a design variable in the horizontal coordinate. You may have a function value in the vertical axis, and basically you have a function. You have a function, okay? And you have no idea where the optimal solution is. You may have a initial guess, k equals to 0, and you evaluate the function value like this. So the value right here basically is this guy, right? And sometimes we just write it like this. Basically, you use the initial guess to plug in and then get the value. And every time we plug in a function and then get a function value back, it's like a one time of evaluating the function. So sometimes we will count how many times we evaluate the functions. Okay, so we call this function call. How many times you call the function. So this is like how many times you call actually means evaluate the function. Why is it important? So let me give you one example, a real example in a motor company. So when I was studying in USA, we worked with many scholars from the universities and also from the company. There are aerospace companies, mobile companies, and I know some scholars from Ford Motors. They are truly doing optimization in their company. So whenever they have a vehicle design, you have maybe 1,000 mechanical parts. Every mechanical part has its own dimension, material property, shape, and so on. So they are all design variables. So if you have 1,000 mechanical parts, you may have 5,000 design variables for the one car itself. So it's impossible for you to consider all 5,000 design variables in one mechanical design because that's too many. So they rely on simulations. But even with simulations, if you would like to try to find the optimal solution set, there are way too many parameters, way too many design variables, 5,000 of them. So they will figure out a way and then try to reduce the number of variables. So how do you do that? Basically, you can make some decisions. Let's say you decide that certain diameter of a cylindrical part is fixed. That's your decision. Once it's fixed, it becomes a kind of fixed parameter. You don't change it anymore. Okay? So once you start to make certain decisions, you reduce the number of design variables. You still have a lot of them. And there's something called sensitivity analysis. So basically, you test how sensitive a variable is to the function. So basically, you are evaluating something like this. Basically, partial derivative. If you change the I design variable, how much change is gonna affect the objective function? Just for the sensitivity analysis. Okay? So if you have 5,000 of them, then you need to do, if you have 5,000 design variables, you need to do 5,000 partial derivatives. And maybe there will be, let's say the objective function is the weight of the vehicle. And let's say one of the design variable is the position of the wheel. If you move the wheel forward by 10 centimeter or backward by 10 centimeter, it doesn't change the weight. So the partial derivative of weight over the position of the wheel is 0. It doesn't affect the weight. Then if your objective function is only the weight, you won't choose position as the variable because it doesn't change. Okay? But the position of wheel change something else. So there will be multiple functions you need to evaluate in your design. Anyway, this is what we need to do in mechanical design. So let's say we are evaluating this. How many times do we need to call the function? So if you use finite difference, this is close to f of a certain value. Actually, I have to do something like this. X plus a small increment, and this is like a EI. What was this? This is like a normal basis. This is like normal basis. So what is normal basis? In the past, we usually handle with IJK. What is IJK? In a three-dimensional, like a 3D world, IJK equals to basically 1, 0, 0, 0, 1, 0, and then 0, 0, 1, right? They are the normal bases to represent the 3D world. And sometimes we can write it like this, like a E1, E2, and E3, right? So what is a vector of EI? Basically a long vector, and then only the ith component equals to 1. The rest of them are 0. Okay? So delta right here is a small value. And you need to do this and then minus this over delta. Right? This is finite difference. So if I want to do sensitivity analysis to study how the objective function changes with respect to a small change of xi, I can approximately compute this. And over here, how many times I call the function. You can see it, how many times? Right? Once and twice. So it's like if you want to know how much change is going to happen by changing the design variable. Oh, by the way, I made a mistake. Here, this is single variate, so no vector sign, sorry. So if I move this finite difference back to the figure on the left-hand side, it's like you are making a small increment right here. And the small increment is called delta. So right here, this is basically x plus delta. right? And then you are evaluating the function value right here. So basically this is f of x0 plus delta, right? And then what you're doing, you're basically estimating the slope. F of x plus delta minus f of x over delta. This is exactly the finite difference right here. And if you would like to know how the function is gonna change, basically you are estimating the slope. So you're computing the slope, right? And the slope basically is partial f over partial x, right? So in fact, if I want to study the slope of a function, I need to call the function twice, not once. So it's like when I have a vehicle design, I cannot handle 5,000 variables because I need to, if I do this, I will be studying for every, so for all the design variables, I compute this 5,000 times 2, right? I compute them then 10,000 times. I evaluate the function 10,000 times. Way too many. So I try my best to reduce the number of variables. Okay, now I made a decision. There are only 5 key variables I'm gonna change in the entire vehicle. Okay, just change 5. So what are the possible combinations for your design? So what students usually do is that, okay, now I have 5 variables, let's see. X1, let me do this. X1, X2, X3, X4, X5, right? Now I want to see how many combinations. So I pick up a range for every variable. So let's say, okay, X1 in the range of from 0 to 10. Okay, X2 from range 3 to 6, and so on. You pick up a range, and then you try to figure out, okay, what's the best value for each variable inside the range. And if you want to try so many different levels in each interval, let's say 10 levels. Okay, 10 levels times 10 levels times 10 levels. Oh, in total you have 10 to the power of 5 combinations. Levels. What do you mean by 10 levels? It's like, okay, from 0 to 10, okay, the first level can be 0, second level can be 1 and 2, and so on. Choose 10 of them. And then I want to combine them. So you need to test 10 to the power of 5 combinations. 10,000 combinations. What does it mean? That means you need to build 10,000 cars and then test all of them to figure out which one is the best. Then the company bankrupt. And so you cannot make 10,000 cars and then test all of them. So you can simulate, put all of them in simulators. So let's say one simulation you think about is a real car. So you must want to test the dynamics, crashing, or many other behavior, fluid dynamics, aerodynamics, and so on. Fluid dynamics, not aerodynamics. So you want to run a bunch of simulations. But in this case, you have 10 to the power of 5 simulations that you need to do. And let's say one simulation costs you 10 minutes. Then it's like a 10 to the power of 6 minutes. This takes forever. Okay? So there are ways to reduce the number of tests you need to do. So let's say you are already having you are choosing 10 levels in each variable, and you cannot do all of them. So there are some ways, you probably have heard of it, it's called the Taguchi method. In Chinese, it's called a 填口法. Yeah, it's like and also another method is called the orthogonal array. If I have time, I can talk about all those, but not today. Just quickly go through. So Taguchi method is a method for you to do basically sensitivity analysis, and then pick up the variables that are more sensitive to the objective function. So you basically fix the ones that is not sensitive. So that's one method for you to reduce the number of variables. Oh, by the way, whenever I do this, that means number. Whenever I do this, that means with. And this is without. Okay? And this is because. Okay? And also, this is with respect to. Okay? So you can use Taguchi to reduce the number of variables. And what's an orthogonal array? Orthogonal array reduce the number of experiments. Okay, these are two very well-known and common methods for master students. So in this particular case, you need to do 10 to the power of 5 combination. That means you need to do 10 to the power of 5 experiments. And orthogonal array can help you to reduce the number of experiments. Let's just pick up 50 out of 10 to the power of 5. Okay, but still a lot. Okay, so in optimization, usually we don't do, we may need to do Taguchi. We still cannot handle too many variables. But we try to avoid doing this orthogonal array. Because orthogonal array is like a sampling method. And this will tell you, where are the locations you sample. You don't sample everywhere. If you do all the combinations, we call this approach full factorial. This is like a full factorial approach, okay? And it's like a exhaust search. Sometimes we call it exhaust search. In Chinese, we will say 地毯式搜索, like searching on the floor. Okay, but in English you call it exhaust search. It's like test everything. Okay, but we don't want to do that. And orthogonal array is like, okay, it's like we are searching on the floor everywhere, and there in one of the tile there's a gold underneath. So it's like, okay, let's search everywhere. But orthogonal array will say, okay, let's search here. Okay, let's search here. Let's search here. Try not to search every tile. So if you think of every tile on the floor, every single tile is like one experiment, and there are so many tiles to search. And if you test all of them, then you are doing full factorial search, exhaust search. And optimization is like this. Okay, let's search this tile. Okay, I want to know the slope. Then I will move a little bit to see how whatever function that I'm studying, how much this function will change if I move a little bit. Okay, I figure out, okay, there are certain function that is having a gradient in the space. I should move certain direction. So optimization basically is trying to find out which direction I should move for searching a solution. Okay, move here, move there. Okay? So back to the mobile company story. Function call is a very important thing for them because every time they evaluate a function, it's like they need to build one car. It's like it's one experiment. Even for sensitivity analysis, to increase certain variable by a little and test for whatever function you are interested in, it's costly. So they cannot build this many cars. They will simulate a lot. They may have different offices, divisions, multiple engineers working on whatever they are strong at. One person working on structural design, the other person works on fluid dynamics, another person works on control. They work individually and then collaborate, and then maybe after a month, okay, that's so far what we can do. That's the best design that we can have. Okay, now let's build one. So they build a car based on whatever they can do the best, and then they really build one. And then for the real car, they do the crashing, they do all the tests. They put hundreds of sensors on top, several cameras, just to capture whatever behavior the vehicle is based on that set of design variables. So the real experiment is like one important function call to evaluate the true performance. And then for after that round of real tests, just one round of real tests, they get real data. They go back and then refine their models, correct everything, and do another round of design process. So for a vehicle company, based on my understanding, the most they can crash is 5 cars. They can only crash 5 times. On the 6th one, they need to mass produce it. So think about it. It's like you have an unknown optimization problem, unknown function, thousands of variables. You can only truly try them 5 times. So it's we try to reduce the function call. Okay, so if you have no idea about optimization, and if function evaluation is free and super fast, we don't need optimization. We can just search everything. Just search everywhere. And then compare, okay, this is the smallest. But in reality, we cannot do that because every test is so expensive. Okay? So that's why we need optimization. Okay. Now, so what does Newton's method do? So besides the first order derivative, which tells you the slope, Newton evaluated the second order derivative. So it also computes second order derivative. So, but in one dimensional problem, actually it's like a df. It's not partial because there's only one variable. So basically, we often just write it like a f double prime, right? So how do you compute this? You can approximate second order derivative by this. This is k. Okay, just for you to know. If you want to, you can prove it very easily. Or you can go online to find it. This is how you can compute second order derivative by finite difference. Over here, you realize you need to compute the function 3 times. One, you compute the function right at the current design. The other one, you move forward a little bit by delta, a small number. And the third, you move backward. You minus your design variable by delta, and then evaluate the function. With 3 evaluations, you can estimate the second order derivative. So it's like you are moving backward right here. And with 3 evaluations, one being here right at the current design, the other one forward, the other one backward, with 3 function evaluations, you can compute, you can estimate the second order derivative. Okay? So basically, this is second order derivative. So what Newton did was, he did a second order Taylor expansion of the objective function at current design. Okay, so how does it look like? No vector sign. So basically, I will just, no vector sign, sorry. I will just use xk for short. So I will just define this as xk, just for short. And then I will be using fk, just faster notation. Okay, so plugging xk plus x minus xk times f prom, but here plug in xk plus 1/2 of x minus xk squared f double prime xk, right? So this is Taylor, second order Taylor expansion. So when you do that, and if you are sure the function is called a positive definite. Positive definite. Basically, the second order of derivative is positive or 0. So in Chinese, we usually say 凹向上. The function is like a U shape, okay? So it's like we call this convex. And in Chinese, we call 凹向上. Basically, what does it mean? It's like a U shape, okay? So why are we looking for a function is like a U shape? Because there's a bottom. The bottom exists. So that's why it's a positive, definitely positive. That positive definitely means it's like definitely positive. Definitely the second order of your derivative is positive. So if a function is like that, then whenever you do a second order Taylor expansion, you will be getting U-shape function. So if you have a function like this random drawing, okay, and then you do if this is your xk, and then if you do a second order Taylor expansion, the function may look like this. I didn't do a good job. Okay. Now it should be symmetric. Okay, kind of. So let's say this is your second order Taylor expansion. Okay? It's always having a bottom. So you can find the lowest point of that approximative function. So the goal is you want your x k plus 1 to be found at the bottom of that approximate function. And then you will be repeating this process again and again until you converge. That's basically what Newton's method is about. So how can you find the lowest point of a second order polynomial? We learned this already. Whenever the first order derivative equals to 0, we have the extreme point, right? That's from high school. And since this function is positive definite, there's definitely a minimum point at the bottom. Then the location of f prime equals to 0 gives you the minimum point. So that's why what Newton is doing is trying to take a derivative of this function and then make it 0. So let's do it. This is a constant, so take a derivative, it becomes 0. And here we have a variable x right here, we have a coefficient right here. After first order derivative, you will have x prime of this coefficient left. And over here we have a square term and an x and a 1/2 in the front. So it's like a 2x times a half, so 1x. And you have a coefficient left. So at the end you will have x minus xk times f double prime of xk. Right? And you want this to be 0. You want this to happen. So let's just solve for this equation, and you hope at the end this guy is your new design. So this is your x k plus 1. So let's just reorder this equation. You will find x k plus 1 equals to xk minus f prime of xk over f double prime over xt. Right? This is how the Newton's equation was derived. And in order to perform the procedure that I have mentioned, the iteration process is gonna be like what I showed you last time. I'm going to write it again. Initially, the initial design, you have basically initial guess. So it's like no vector sign here. Some value you guessed, and k starts with 0. Okay? And then you will be computing for f prime of xk and f double prime of xk. How do you compute it? Usually finite difference. So I can write down the finite difference equation again if you want. Okay, and f double prime of k. This is how you can compute it. Then implement the Newton's equation. I'm being lazy, so using the shorter sign there. And convergence check. Convergence check. Usually you put a sign like this, right? And if not yet converged, if it's no, then k equals to k plus 1. If yes, converged. The last one is your optimal. That's the standard optimization process. You can even find this kind of flow chart or solution process in research papers. Sometimes researchers is kind enough to show you this. Okay? But how about 3D problems or multi-dimensional problems? So now I want to quickly move on to multi-dimensional. Sure, so right here, multi-dimensional Newton's method. Yeah, I know it's tiring. Okay, someone is doing yawning. Yeah. Okay. If you have difficulty falling asleep, just do some math before you go to bed. You can have a good sleep. Okay. So what you're going to do is second order Taylor expansion again. But this time, multivariate. Up to now, you realize I have been trying to show you multiple terminologies, because those are the terms that you can see in research papers. I try to describe things in different terms because some researchers use this, some researchers use that. I try to show you many of them, so you can find research papers more easily, and also whenever you write, your article won't be too boring. Sometimes you can use this word, sometimes you can use another word. Okay, how do you do that? So now you need a vector sign, because it's multivariate. Second order Taylor expansion, right? So you will be plugging in the kth design variable, and then x minus xk. Now dot product. This is very important. Dot product, and over here gradient. I will tell you more later on. Plus 1/2 x minus xk. Because it's vector, you cannot do square anymore. You have to do dot product. Some matrix cohesion. I will tell you what that is later on. And then again, dot product. So this is the gradient. In Chinese is T2. Okay, and Hessian. This is called Hessian matrix. In Chinese, people call it 海参矩阵. Okay, so for you to know, Yeah, but what are they? So gradient basically is partial f of partial x1, partial f of and partial xn, if there's n of them. What's Haitian? Haitian basically is like this, partial f squared and partial x1 squared, partial square f, partial x1, partial x2, partial square f, partial x1, partial xn, and the last one is this. Okay. Basically, it's a container of all the possible second-order derivatives, including taking partial derivatives with a first variable and the other one. Okay? So, if you, I'm not sure if should I do this? Yeah, let me try this. Okay, so, for a vector dot another vector, okay, you can actually write a vector in a different form. Summation AI EI. I goes from 1 to n. Do you agree? Okay, let me show you. Usually it's like this, A1, AN, right? And in the past, when you have a vector like 1, 2, 3, there's another form where you can say 1 times I plus 2 times j plus 3 times k, right? And you can write in this way, E1, 2E2 plus 3E3, right? So what is this? This is basically a summation of AI, EI, but now I goes from 1 to 3, where A1 equals to 1, A2 equals to 2, A3 equals to 3. So now you agree a vector of A can be written as this guy, right? So you can say, here is B, J, E, J. So here I'm going to use J, okay? You can do that, right? But Newton, no, not Newton, Einstein. Einstein is a very smart person, mathematician. He derives math, and he, of course, works on dot products. Whenever he's deriving something like this, he needs to write a lot of summation sign. There's too many of them. He's becoming lazy, so he invented a way to make this notation simpler. So he's smart enough, he can visualize something in his mind. He doesn't need to read this, he doesn't read the whole thing. So for Einstein, he writes it like AIEI dot EJ. He doesn't write the summation sign anymore. So this is called Einstein convention notation. I think it's like some kind of convention notation. Is it called convention? or Einstein's notation? You can Google for it. Let me just double check if it's called that. times, is it called convention or something? Summation? No, there's or just Einstein notation. I don't. Is this called convention? Oh, basically summation, not convention. Basically summation notation. Oh, okay. Or just Einstein's notation. Okay. So what's gonna happen is whenever you have an index, two repeated index in one term, there is a summation. So that's how you read it. That's why over here you need to replace the index by a different one. You use a j right here because this vector is having its own summation. This vector is having its own summation. They are different summations. So if you use I and I here and also I and I here, when you ignore the summation sign, it will be confusing. You have no idea which one is which the summation is representing which kind of summation. So why do I do this? Because later on it's good for my proof. Okay, so once there's this Einstein notation, there will be some math. And I will tell you some math right here. EI dot EJ equals to this. What is this? This is the Kronecker delta. You can Google for it. This is called the Kronecker delta. And what is Kronecker delta? This equals to 1 when I equals to j, 0 otherwise. Okay? So, this can become, look at this part. I should say, look at this part and this part. A, I, and B, J, they are just constant values. They can be moved together. So you can rewrite this as A, I, B, J. And the rest is E, I dot E, J. And this guy is Kronecker delta, because the math right here. Do we need to prove it? Let me show you. If E1 dot E1, like a 100 dot 100 is 1, right? E1 dot E2, it's 100 dot 010, it's 0. So basically, and over here you can see when I equals to j, this equals to 1. So here's just to show it makes sense. Now from here, this equals to A, I, B, J, and Kronecker delta, Ij. Because Ei dot Ej equals to Kronecker delta Ij. And what's interesting about Kronecker delta is you can swap the index when you put a constant and a Kronecker delta together. So what's going on is whenever you have some constant terms in the front, Well, basically there are three constant terms multiplying with each other. Whenever you have a exact same index somewhere in your multiplication, you can swap the coefficient, the index here with the other index in the Kronecker delta. So here, this equals to bi. So swapping. Here, because of this bj has the same index with the Kronecker delta ij. So the index of bj can be swapped with the other index in Kronecker delta, which is I. So you can do index swapping. So this becomes AIBI. And when you have AIBI, what can you do? Based on Newton's notation, it's actually summation I goes 1 to n AIBI. Is it true? This is basically A1, B1 plus da 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 da, AN, BN. Isn't that the result of dot product? From here to here. Right. So this is how Einstein derived math. Okay, and it will help me to do some math in the later on, the further derivation. Okay? So if you are in the solid mechanics, Einstein notation has been used a lot in solid mechanics. So if you are in the field, you are working on solid mechanics or fluid dynamics, they use Einstein notation a lot. Okay, now back to what I want to do here. If I can use this the Einstein notation, then something interesting is gonna happen. So let me just copy this and paste it here. So I can rewrite this as this is Fk, this is fine. And this one becomes xi minus xki. Let me just use bracket k so you won't be confused. The k right here is representing the index number. So I don't want you to be confused with the subscript index for I variable. And over here, EI, right? Dot product. And basically, this is partial f, partial xi. This is basically partial derivative. And of course, you plug in the k variable. But here, because there's a dot product, so I want to put this is xj. I want to change the index to j. And here is ej. Okay, and then what's interesting is here, 1/2. So let me move to another line. 1/2. After a plus sign, you can restart the same index again. So xi minus xi, but the k for the kth variable, and ei dot product. Okay, the Hessian matrix. I didn't talk about matrix. Here I just use a capital H, but here I used J, I, J, K, L, M. Let's use M. JM, and here I will tell you about this EJEM. I'll tell about this later on. And then dot product with another X, here I need another X. I use N already. Let me use P and Q. Let me use P and Q, so not the N. Let me use P and Q. Here's P, and here's Q. XQ. And EQ. Okay? So what's going on with this guy? Okay, so take a look at a matrix. If I have a matrix, it's like A11, A12, A1N, ANN, right? And for Einstein notation, or let me write it like traditionally how you can describe this matrix in with normal basis. So it could be written as I goes 1 to N, J goes 1 to N, Aij, and then Eij. Actually, in the same fashion, for vector, you can write it as the summation of Ai, Ei, but Ei is a normal basis. But for matrix, you can write it like this. So here, you put two normal bases together, then the I and J represent its location. Okay? And the Kronecker delta calculation behaves the same for the same way of you write a matrix. Okay, so let's see what's going on. So over here, I'm gonna do some magic. So if I have a vector dot a B matrix dot a C vector, so traditionally what we do is we have it's actually A transpose multiplying B matrix times C vector, right? This is what we usually do. And what you are going to do is you have A1 dot 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 AN multiplying B11 dot 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 B1N dot 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 BNN, and then multiplying C1 dot 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 Cn. This is what you usually do, right? So you will have terms such as A1, B11, C1, da da da. You have a lot of terms. So what Einstein notation is good at is doing derivations like this. I want to show you. So if I avoid using matrix multiplication, I will use Einstein notation. This is gonna be like AI, EI, dot product, B, J, K, EJ, EK, right? Dot product, C, I, J, K, L, EL, right? So this guy is this guy, this guy is this guy, and this guy is this guy, right? I didn't violate anything I have talked about. I just show you how you can put them together. Now, what's interesting is that you can now take a look at which are the coefficients. These are the coefficients. They're just scalar. Scalar can be moved anywhere. So now let's move them together. So A, I, B, J, K, C, L, they're just put together. They're scalars. But the rest will be the normal basis. E, I, dot, E, J, E, K, dot, E, L. The order of those normal bases and the dot product signs are important. You cannot randomly swap them. Scalars you can, but the vectors you cannot. So keep them, but keep them in the same order. Now take a look at this guy and this guy. isn't this Kronecker delta ij and this Kronecker delta kl? Right? Yes, they are. So now, at the end, you can do the index swapping again. So over here, there's an I, there's a J. So okay, this J, they are having the same index. So I'm gonna swap the J index in B with I. So this one, swap to I. Okay? Now, there's a L, same index. So this one, swap to K. Okay, swapping. So now at the end I have A, I, B, I, K, C, K. What does this mean? This means double summation. I goes 1 to N, K goes 1 to N, A, I, B, I, K, C, K. This directly tells you how all the terms is gonna look like. This is the result. And for Einstein, he doesn't look at these. For Einstein, he just look at this. Okay. So if I can do that, this one can be greatly simplified. So I'm gonna copy these. Copy. And then paste it here. Gonna move this. And then I'm going to do the Einstein notation magic. So here, Fk plus basically xi minus xik multiplying this. After swapping, this becomes I. So I'm already doing Einstein notation because the EI dot EJ equals to Kronecker IJ, that swaps the J to I. So at the end, only I right there. Okay, and then plus 1/2 of xi minus xik. Here I can keep the P, IP, and then xp minus xpk. How come? From here. Okay. So now, what does 1D Newton's method do? You do a first order derivative and make it equals to 0. So let's do that. First order derivative. And this is a constant, so disappear. Over here, only this guy is a variable. So take a first order derivative. Oh, sorry. Not f prime anymore. It is multivariate. So when you do first order derivative, it's actually partial derivative. So you are actually doing gradient. So you are actually you are looking at partial f of x, let's say xi. Do I use the same index? Yeah, I think it's fine. Okay, I just need to be careful. Okay, so for multivariate, when you are looking for the optimal solution, the minimum one, you take the first order derivative, but for multivariate functions, the first order derivative is a vector, basically the gradient. And the gradient vector has multiple terms. This is the ith term. I goes from 1 to n. So partial f, partial x1, partial f, partial x2, partial f, partial x3, and so on, n of them. So I'm just talking about the ith component of the gradient. So let's do that. Here again, this is a constant, so when you do derivative, disappear. Now there's a xi, so when you take a first order derivative with respect to xi, of course what's left is the coefficient. So now you will have this guy only. The coefficient. This is the coefficient. Right? And plus, over here in the back, there's a variable, there's another variable, and let's say we take a first order derivative with this guy first, then you will have like a 1/2, and then xip, xp minus xpk, right? And you need to do, because p sometimes is equals to I. Whenever p equals to I, then you need to take the derivative of this guy. Because remember, this is a summation. So you will have, when this I equals to p, then the derivative of this guy equals to 1. So when you are taking derivative with this guy, then the same coefficient happens. So this term, you have two of them. But when you are taking derivative with this guy, you are having HIP, and you have summation, the second index, summing the second index with xp. But when you are taking derivative with this guy, you are summing the first index with this guy. So there's an assumption. This H matrix has to be symmetric. So it's transposable. So HIP equals to HPI. So then you can have 2 times of this term. So from here you can easily see HIP may not be HPI, but if it's happening, then you have 2 times of this term. So the math will look like the one-dimensional derivative. Okay? So you need H to be symmetric. Right? If I take it slow, you will have another term where you are doing this, xi minus xix, and then hip. So, because when you are doing partial derivative, you do a partial derivative with this term first, plus another time you are taking partial derivative with this term, right? So you have 2 terms. And previously, for one-dimensional functions, these 2 terms are the same. But now, they are not the same. So first time when you take partial derivative with this term, the coefficient is left. So these are the coefficients. Second time, here are the coefficients. So are they the same? They are the same only when this H is symmetric. So since H symmetric, which means HIP equals HPI. So these two terms are the same. So this becomes K this time I would like to write it like HIP XP minus XPK. 2 times of that. These terms becomes the same. So this is partial f of partial. And you want this to be 0. You want this to be 0. So at the end, what you can do is you can reorder everything. You will have HIP XP minus XPK equals to negative. Okay, in Einstein notation. Here, sum in P. Sum in P. This is Einstein notation. Einstein. Okay? But in fact, you can recover it back to this. Oh, I forget the K here. All the H is having a K. Plug in the K variable. So all the H has a K. Here. So basically, it's like this. Here becomes gradient, right? If you recover it back to the matrix form, then because this is a square matrix and also symmetric, when you pre-multiply the inverse of it, it becomes an identity matrix. So you can do this. Inverse of it, dot product, right? You pre-multiply the inverse of A. So this part becomes the big I, identity matrix. But on the right hand side, you have this pre-multiply inverse of Hagen. So at the end, that's the Newton's method equation for multi-dimensional problems. And of course, this is for, why do we do this? We are looking for the k plus 1 variable. So we use the current design, we evaluate the gradient at current design, we evaluate the Hagen at current design, plugging into the equation, it tells you what's the next design. Multivariate new design. Okay, so what would be the solution process look like? So initial guess, you have a x, k equals to 0, k equals to 0. You guess a vector. You compute for gradient f, basically plug in xk, and you compute for the Hagen, plug in xk, and then you apply Newton's method, xk plus 1 equals to xk minus the Hagen inverse, dot product, gradient. Oh, yeah, that's fine. And then what? Convergence check. If not yet converged, no. K equals to K plus 1. If yes, the optimal solution is a vector equals to the last one. That's the solution process. Okay? I didn't talk about the convergence check. Let me tell you about them. There are some common convergence checks that you can do. Convergence check. For one dimensional, you can do the difference of K plus 1. Oh, let me just use the shorter notation. If the difference between the K plus 1th variable and the Kth one is a small number, smaller than some number, let's call it epsilon. If this happens, we stop. Or sometimes people do f of k plus 1 minus f of k. So if the function value has no change, then stop. So if you have a function that is having when does it happen? Okay, very flat bottom, and you move to somewhere. Actually, I think both of them will happen at the same time. Because if your bottom is very, very flat, then the gradient is very small. So your movement will be very small. Maybe there are some algorithm allows you to move your design point forward, but even when a function is very flat, which means the function value doesn't change too much, but the algorithm maybe allows you to move forward with a big step. Even with a big step, x changes, but function value doesn't change too much. And you can say, okay, I'm done. I cannot find, even with a big jump at near the optimal, I have a big change of x already, but function value doesn't change too much. I decide to stop. So from here you can see you can either use this one or this one, and sometimes you can say both. You can use both of them. You can have multiple checking criteria. So I would say and or, right? You can have either one of them, or you have to satisfy both of them, or you can have multiple of them. You can say, okay, either one of them satisfy, I stop. Or if all of them satisfy, I stop. So you define the criteria. There's no standard way. You decide it. Okay? And some others may do this as well when k is already equals to k max, the largest iteration number that you will allow. Because k starts with 0, right? So whenever you move up to here, right here, k is 0. And if it doesn't converge, you move up, k becomes 1. Goes up to here, okay, k equals to 1. Another round, k equals to 2, k equals to 3. And you can say, okay, when k equals to 10, I stop. So sometimes people just don't have the enough resource to do itemization to the infinity times. They can only allow 5 times. So sometimes people use iteration number, maximum iteration number as the determination criteria. Okay, and these 3 are probably the most common ones. Okay, and you can mix and match. How about 2D? Or I should say multi-dimensional, multi-D. In that case, people usually do this. They compute the so-called two norm. This is, in English, is called a two norm. What is a two norm? Two norm of a vector basically is the length. Okay? The length of the vector. So basically you compute its length, which means it's like a distance between the two vectors. Or they do the same thing. Because f is a scalar. Scalar has no, you don't put two norms for scalar. And or k equals to 10x. Okay? Let's take a short break, and I will be back when, if you have questions, you can let me know. Take a short break. Okay, this time I'm right. Okay, right? Yeah, so if I make a mistake, remind me. So from here you can see gradient is 0 already. Right? So plug in x of 2 equals to x of 1, which is 5 over 2, 1/3, minus Asian dot product 0, 0. So of course, you will get exactly the same result. And this time, the new design minus the previous design equals to 0. It's, yes, smaller than a very small number. Yes, converged. So, x star equals to x2, which is 5 over 2, 1 over 3. Yeah. Oh, yeah, you're right. So I made a mistake. Where? Here is where did I make mistakes? Huh? Why? Oh.
12 into 2 plus 4.
This is 28.
Yeah.
Okay. So it's only 8. It's only 8. So here's minus. Minus. So here's minus sign here. That's why it's 0. So okay, here minus. Correct? Okay. Thank you. I told you I made mistakes. That's the solution process. Any questions about multi-dimensional Newton's method? Okay, so we have some time. I can do some coding on MATLAB. So let me finish this. Stop recording. And then move on to desktop. Laptop, not desktop, laptop. So I have 25% of power. I need to complete my coding within 25% of my power. Okay. Yeah. 74% of battery. Okay, desktop, that's fine. New script. So usually I will start with clear CLC and close all, which means clear the memory, clear the command window, close all the figures. Okay, and then we will have, I like to use symbolic, so sims x1 and x2. Okay, and then I will say my objective function equals to 2 times x1. Oh, and let me use the same, or anything, that's fine. X1 squared plus 10 times of x2 squared minus 6 times x1 plus 4 times x2. So some problem, some math problem, but in a symbolic format. So symbolic in Chinese is called 代数. So symbolic function. So you can easily plug in numbers. Now I need to create a variable. I'm gonna use capital X. Oh, I need the iteration number k, but in MATLAB the index number cannot be 0, so I will start with 1. K equals to 1. So I will have a capital X k, and I'm gonna use multiple rows as different design variables at different iteration. So k 1 comma how do you call this? No, how? Column sign. Is it called column? Okay. That means the first row. So this is my initial guess. Let's say 5 and 5. Okay. So this is initial guess. Okay. Let me create a value called error. This is for my convergence check. For convergence check. Then while loop. While error is large, 10 to the power of negative 3. While is large, I will continue. So this will stop when error is small. And over here, I need to evaluate the gradient. So the gradient equals to, I will keep, actually just gradient. And then I need to do partial derivative. So DIFF means partial derivative f over x1. Okay, and then I need to substitute numbers into it. So subs is substitute. And how do you substitute? There's a unique way. This is called a cell, x1 and x2. And then current value. So the current value is k comma column, right? So this is basically partial derivative of f with respect to x1. Plugging in whatever you have, plugging into x1 and x2. But this is the gradient vector is a vector, so I will have a second line, which is the other part. Partial derivative with respect to x2. So this will be my gradient. So save this file and see if it's correct. So let me call this optimization, optimization. Today is 02/24/2025. Okay, and you can test it. Oh, something is wrong. Yeah. one more bracket. Oh, save. So run the code just to make sure I am coding this right. One step forward. So the gradient is 4104. Should be right. Okay. So it's a vertical vector, right? Now I need to compute the Asian. So for the Asian, it's gonna be similar to these but different. I'm gonna do H11, H12, and H22. So and then I assemble them. So similar, but one more derivative. So DIFF again, DIFF again, and then comma xy. So taking the derivative twice and then substitute, right? So here, that's all. And then my Asian will be H11, H12, second line, H12 again, H22, because it's a symmetric. So I don't need to compute H21. Okay, call this Asian. So my next design will be K plus 1 comma equals to the current one, K comma minus inverse. How do you inverse? You can say Asian, and then this will be inverse in MATLAB. And multiply gradient. Okay? And then you need to evaluate whether it's convergent or not. So error equals to norm, basically to norm, the current design minus the new design. K, and then over here, K equals to K plus 1. Boom. Something's wrong. No, this is not how I do inverse. How do you do inverse? Oh, okay. I got it. I think I need to. Let me make sure I'm doing this right. Step in Asian. Can I do this? Oh yeah, I can. I understand now. Because my vectors are supposed to be vertical. But when I initially designed this, they are horizontal. So let me just call this, I need to transpose this guy. Or let me just make it vertical. This should be vertical vector. So in that case, it's like this. Okay? Make it vertical. So here, it should be like this. Now they are vertical. Just follow the orientation of the math. Okay, what else? Here should be vertical. Okay. Vertical. See, is everything okay? Yep. So what's the solution? The solution is 3 negative 0.2. That's the solution. So initially 5. After one iteration, 3 and negative 0.2. Another iteration, 3 and negative 0.2 conversion. But how are you sure it's right? So let me plot it out. So figure, and then easy contour F. I need to choose a plotting zone. So negative 10, negative 10, 10, and 10. And hold on. And X is equal set GCF color white. Set GCA font size 15, and then once you have your initial design, plot it out, plot X first one and second one, X1 and X2 basically. Let's draw a black circle with a line width of 2. Oh, let me make this line width with 2 as well. And marker size of 8 maybe. Okay, and whenever there's a new solution, let's plot it out. So here 1 of k plus 1. Here k plus 1, and then let's draw a line to show you the iteration, the movement. Let's draw a line. So plot. Similarly, so here draw a line. So it's like this. Okay. Then 2 comma k, right, and then draw a straight line. So minus means straight line, red color, line width 1, no need marker size. Okay, run. Oh, something's wrong. What did I do? Easy serve, easy contour. Sorry. Should I do this? Oh, what? X1 1 and X2 1 line with marker size. Not maker size. Typo. Okay, that's what happened. So it happened too fast. Maybe we pause right here. Pause. Pause right here, and then pause right here. Okay, that's the initial point. That's the first iteration. Second iteration conversion. Okay, so from here you can tell I have drawn the contour of the objective function. It's like a ball, but it's not circular. It's like an elliptical ball, right? It's if you cut or make horizontal cuts, they are ellipse, 椭圆形, and you have an initial starting point. Newton's method will figure out the gradient and Hessian and tell you, ooh, boom, goes to somewhere. Okay, let's change a different function and see how it goes. Let's say let me also show you how it looked like in a 3D world. So let me call this figure 1, and let me draw a figure 2, and now we can do easy surf. Easy surf. We do exactly the same thing. Yep. And then when I do the drawing, I need to specify this is for figure 1, and then for figure 2, I will plot out where I show you in the 3D world. So in this case, I need to substitute the current point into the function, so I know, okay, x, y, and function value, right? I need to know the function value just for plotting purpose. So I will plug here, but no derivative. Like this. Da da da. Like this. This is the third variable. I plug in x, y, x1, x2, and then plug in. So it becomes a 3D point. Okay. Now the way I draw it, I think it's gonna be a dot, a huge, and the marker size should be larger. I think maybe 15. Yeah, okay. Then in the 3D world over here, figure 1. Okay. Do the same thing for figure 2. But now, oh, this is plot 3-dimensional plotting. So plot 3. But here I need to plug in. I need to do similar things. Here, I'm going to plug in, so k plus 1. Okay. And I want to draw the red straight line is for you to see how where the movement is. So 3D world, yes. I'm doing this. Da, da, da. So I need a bracket here, and k plus 1, yes. So same thing, but just k, like this. And line style is like this. Should be fine. Okay, do it. Oh, you didn't stop. Oh, hold on. Easy serve. Serve. Okay. Typo again. Oh. I better not do the axis equal because the scale of the variables between the function value and the variables are just different in different orders. So it looks weird. So I don't do axis equal for 3D. Okay, do it again. I need to break it and then run the code again. Yep. So if you visualize in 3D, it's gonna be like this. And where is the design point? Let's see. Here. You see? It's not large enough. Let me make it a different color. Make it, or make it larger. 25. Oh, I didn't do the same thing for here. Okay. Maybe 2 here. Okay. So for 3D, here's a design point, right? This is how the function look like. And if I make contours, horizontal cuts, this is how it look like in the 2D world. And then continue. So one step forward in the 3D world, you move, you see it, from here to the bottom. Right? This is from the top. Okay. You move to the very bottom. Okay? Because Newton's method figure out the gradient and the h. Okay, so let's change a different function, a very nonlinear function, and I guarantee you, I'm not guarantee you, I'm gonna show you the weakness of gradient-based approach. When your objective function is very nonlinear, let's say I multiply this with sine x1 plus x2, some very nonlinear function. Right, this is very nonlinear. In that case, the Newton's method won't converge well. So let's see. So with one step, okay, where did it go? Okay, it was here. It was here. Okay, it moved to. I'm not even sure if it's the function value is dropping. Okay, let's continue. Okay, it's going to move out of the plotting space. Oh, it moved to somewhere crazy. So this one is too nonlinear. Sorry, I will make it easier for Newton's method. Just maybe not multiplication, maybe just plus. Okay, not enough. Not enough nonlinearity. So maybe 100 times. Okay, 100 times. Okay. Let's see. Yep. Okay. It's interesting. It's like a spiral shape. Let me start from here, from -5. I think it will show better. My initial guess, I want to change it to -5 and 5. Okay, start again. So now this is how it look like in the 2D contour, and this is how it look like in 3D. Because of this weird spiral shape, I don't even know what's gonna happen. One move, okay. Because of the gradient, it's actually moving this design process to somewhere really far away. So it's gonna stop somewhere. Let me see how you can. Maybe not. This is too nonlinear. too nonlinear. So maybe just 20 times. Okay. Maybe this is better. Just a little nonlinearity. Okay, let's see. Good. Okay. So from here you can see it's trying to the gradient, and so it's a second order Taylor expansion. So based on the second order Taylor expansion at that particular point, the convex function has a bottom right here. Okay, but it actually moved from here is one groove, like one groove area. There is another groove area. It actually shifts to another groove. Okay, and let's continue and see what happens. So it starts to move at this local, and then continue. And I think I can, because I used the pause, I have to, okay, finish. So you realize it actually stopped right here. It stopped right here. So the Newton's method will take a move from one area to another area, and the following gradient allows it to converge somewhere at the bottom, but it's not the real minimum. You can see it's a local minimum. It's like you have a slide, and you know nothing about how the whole field look like. You can only rely on the gradient at the local position, and the equation allows you to move toward a certain direction and with certain distance, and then stop, and then evaluate the slope again, and then do the slide again. So it doesn't tell you there is a lower point right here. Newton's method doesn't explore this place. It doesn't know. But sometimes when the slope is getting smaller and smaller, it tends to slow down and then stop. So gradient-based method has a disadvantage. It sometimes will converge at the local minimum. But globally, the true minimum is maybe right here. So we call the local one local minimum. The true minimum, we call it global minimum. Gradient-based approach doesn't guarantee global minimum. Sometimes it just jump around and then converge somewhere. Okay? So later on in the future, when we learn a very different method called evolutionary optimization, it relies on some kind of random process. It doesn't evaluate gradient. It just randomly search. It's like firing multiple shooting stars, and then just like a firework. Okay, just go everywhere and then search very randomly. Sometimes it will bump into some local, which is not the optimal. But sometimes if you're lucky, if that random process is lucky enough, or if you search for the space long enough, you may end up with the best one, the global minimum one. Okay? So that's it for today. I will, as I mentioned, I will give you some recommended homework. You can do it, but you don't need to hand in. Okay? And I will give you this sample code. I will give you this code. So basically, I will just give you the code. So what's the homework for today? The recommended homework for today. You just give some problems to the MATLAB code, run it in MATLAB. It helps you to visualize it. It even show you the values during the process. And then you solve it by hand, compare with the MATLAB code. Okay? But be aware, you cannot provide this code with some so-called concave problems. So convex. Let me write it down here. Convex is like a second order derivative is positive, right? And we call concave problems is negative. So for the convex, like I said, it's like a U shape, there's a bottom. But for the convex problems, it's like an opposite U shape. So the bottom is at the infinity, negative infinity. There's no, the minimum doesn't exist. Okay? Negative. Okay. So you cannot tell MATLAB code, provide a concave problem to the MATLAB code. You won't stop. I can show you. So let me just get rid of this. How do you make it a concave problem? Just make it negative. In this case, let's see. Let's just run the code. Okay, now it's the opposite U shape, going down, right? And you can tell where this is the initial gas, right? And from here, if you still use the Newton's method, it will start to move toward the infinity, a negative infinity. One step. Oh no. How come? How come? Wait. It is supposed to move toward. Because it's a simple problem. It's a simple polynomial. Is it? Yeah, because the Haitian corrects it. So if it's a messy, it's a more nonlinear problem. Let me try it. Let's say it's sine x1. Okay. I don't think it will move to the right direction. It does. Hold on. It does. But it's not a minimal. Yeah, so for Newton's method, because it was derived by first order derivative equals to 0, so it tends to move to the extreme point. So the Haitian tends to move to the design point to the extreme point, and it will be moving to here. But however, if you want to minimize this problem, you are actually maximizing the problem. And later on, we will have some other methods. It's purely following gradient, and the gradient direction will not be corrected by Haitian inverse. So in that kind of gradient approach, it will go toward the negative infinity and doesn't go back. Okay, but for Newton's method, because the way how we derive it, we have a pre-multiplying term, the inverse Haitian, in front of gradient. So it will move toward the position where f prime equals to 0. That's why it's still going to the extreme point, even when you have a concave problem. But even it converges, but it's not converging in the right point, because if you truly have a concave function like this, if you want to minimize it, the solution should be down there at the negative infinity, not at the top. This is becoming maximizing. Okay? So, I will send the code to you. I will just save it like this. And if you want to practice, you can just change some numbers. And then just work with polynomials. Solve it by hand. And check the solution with the code. Okay? So I will stay here for a couple minutes. If you, let me do the attendance check. So Shin-chan is here, right? Tran is here. Rati, okay. Boru not here, okay. Shen Bing, okay. Zim, yes. And Guan Yu, no. Menace, okay, you're here. Okay. Good. So Let me show you the grouping again. So Xianchen with, let me just do this. So you two are the same group. So I tend to put the, you guys are working with my students. Okay, so please check who you are, who your teammates, oh, wrong, who your teammates are, and then the PhD students work along, okay? That's a grouping. And Junze and Fan Ping, you please figure out who is your teammate. Okay? And also, I will send you, I'll send the code to Tajiro later on, and she will post it on Facebook. And also Moodle. So whenever you post in Facebook, post on Moodle as well. Okay. Okay, any questions? Okay, that's it for today. Bye bye.